Hi everybody, welcome to my 9th axial bar video. In this video, I'm going to be working through this example here with this axial bar hanging off the ceiling. I'm going to work through how to find the internal normal force and also the total elongation. If you want to know something else about axial bars, feel free to check out any of my other axial bar videos. Okay, so when we're solving this problem, the first thing we need to do is to find all the components of this equation here. Alright? D delta equals to n as a function of, what are we going to call this a function of? Because traditionally, well, not traditionally, but previously, we've always done it in the x direction because our bars were sideways. Alright, but in this case, it makes sense to do it, up and down like this. Y, let's just use y. So n is a function of y, dy over e a. Alright? We could call these functions of y, they're just constant functions of y in this case here. Alright. And let's not forget, this thing here has a total length, L. Okay, so let's make a free body diagram first, because like usual, that's the way we do it to find the internal forces. So we'll make a cut at a distance y up from the free end of the bar here, and we'll get ourselves a free body diagram happening here. So it's of length y. And over this length, y, we have some load due to the weight. Alright, and it's going to be some sort of like constant load. Okay, so we can draw that by a few arrows that are approximately the same length. And it's going to be some function of y. Weight is a function of y. Alright, now that weight as a function of y, it's going to be constant, but we can still say it's a function of y. Okay, and then in reaction to this weight, we're going to have a normal force. Alright, just to keep this whole thing in equilibrium. Alright, now, don't forget our directions. In this case, it's especially important because we're doing something different than the normal. Sum of the forces in a y equal to 0. Alright, so we've got n going up minus this because it's going down. And now here we got to be a little bit careful because we haven't defined what weight as a function of y is yet. So if it's constant, we can just do weight as a function of y times y, newtons per meter times meter, done deal. But what if it was something that depended on y? So let's say it was, something and then y squared. Alright, the way we would find the total force here due to the weight, we'd have to integrate, right? Basically the sum of all the individual forces that we can approximate as being constant by taking little slices dy. So it's the weight per length times dy equals 0. Alright, now let's move on and find out what is weight as a function of y. So it's going to be units of weight per length, right? So newtons per meter. And the total weight we have, the total length we have. So wouldn't the total weight per length just be weight divided by length? Yeah, it turns out just to be just that. The total weight per length is just weight per length. So say the total weight was 1,000 newtons, length was 10 meters, the weight as a function of y would be 100 newtons per meter. Alright? So let's put this back into this equation and integrate it out to see what the normal force as a function of y is. So it's weight per length dy integrated. Weight per length, that's constant, that comes outside. We integrate just dy, and as a function of y is weight times y over L. Have to box it off. Make a little reference on the side. It makes it easier to come back later and find the answer if you have lots of pages. Alright, now let's go into finding the elongation of this thing. So basically we took this equation here. So we have n as a function of y. We know e is a function of y, it's just constant. And we know a is a function of y, that's just constant. So we can go ahead and express the elongation of this thing. dy is equal to n as a function of y, it's wy by l dy over ea. Alright, so to find the total elongation, we have to integrate over this full thing here. So from y equals 0 up to y equals L. Alright, so I'm not going to plot this, so I'm just going to go straight into the definite integral with, real physical limits. Y equals 0 to y equals L, y equals 0 to y equals L. Oops, this should be a delta. Alright. Okay, so let's just take a look at this side of the equation here first, because this is kind of a tricky piece in this question. Alright, so if we evaluate this, d delta, the limits did depend on delta, so this can be delta at L minus delta at 0 equals whatever this is we'll get to. Alright, now the delta at L, what is that going to be? Alright, because we want to know, we're always integrating from the base, alright, the base of something out to the end of something. So the delta at y equals L, in this case, that's going to be 0. Because when y equals L, it's at the fixed base here, so that's not moving. So delta L, that's 0. Alright, now the delta at y equals 0, well, that's going to be moving. So that's the delta we want to know. What is the delta at y equals 0? Okay, that'll be right here. Now in most cases, it's going to be the other way. This is going to be the one that's 0. But you still got to be careful and check. You're integrating your delta, you're summing up all your delta from some point to another point. It's usually from the fixed point out to the end. You usually go from here to here. But in this case, I defined y to start here, from the free end out to the fixed end. So this is going to be a little bit different now. Alright, let's go ahead and integrate this side. It's going to be w over L E A integral y dy, right? Because all these are constants. They don't depend on y. Integral of y dy, that's just y squared by 2. So the total delta at y equals 0, take the negative, put it on the other side, we get negative w y squared over L E A, and that's y squared by 2. And the limits are, of course, y equals 0 to L. We evaluate this from y equals 0 up to y equals L. When y equals L, we get negative WL over 2EA. When y equals 0, it's this minus this. Y equals 0, the whole thing's 0, so that's just the answer right here. Total elongation of the bar. Alright, so just to recap, alright, I just want to emphasize process once again, because if you have the right process down, you'll get the answer right 90% of the time or more. Okay, so nice clean initial picture. Alright, we show where we cut, we define a coordinate system as being y in this direction, and that's reflected in the way we took our equation. We realize it's a differential equation because our weight, it's not applied at one point, it's like some sort of constant. And I also want to just quickly note here, if you have some sort of force per length, it's not a good idea to put the force, evaluate the force as like a number and then just plunk it in the middle or something, because that more often than not will get you to the wrong answer. Alright, so sometimes you get the right answer if you take all the force and concentrate it at one point, let's say the center of mass. But more often than not, you have to be careful because a weight per length will give you a different elongation than just, the total weight placed at one point. Alright, then we made a free body diagram. We labeled it, did the sum of the forces. Then we went to the elongation here, and we realized that the left-hand side of this equation is very important in this case, because we're integrating from y equals 0 up to the base. And in this case, this base is not moving, and the bottom is. So then you have to cancel out this term and not this one, making this whole answer negative. And then we evaluated, found it to be this. Alright, hope this video helped you guys out. Thanks so much, and we'll see you in axial bar video number 10.